And of course, the statement of the UN Secretary General in September 2018, as you hear and as you see in this on this screen, is very much the reality. So we in Europe. So I thought that I'll be a little bit biased now towards our own continent, in contrast to the previous speaker, who gave, by the way, a fantastic presentation. I'd like to focus on us in Europe here. So we've got a kind of conundrum here in Europe, the energy resource conundrum. Europe owns only a minute amount of world's proved reserve of oil, gas, and coal. 0.4, 0.86% of oil, gas, and coal, respectively. So, of course, Europe relies on imports for most critical materials to drive the prosperity in our economies here in Europe. So the big European paradox is that we enjoy the best quality of life on Earth, but our inevitable, enviable prosperity is based on energy and mineral resources that are coming from other continents. And this is in itself associated with a big problem, with a big carbon footprint, and of course the energy security in Europe that really needs to be considerably strengthened, because we don't really have these resources that drive our prosperity. Of course, as you probably know, perhaps you don't think it every day, I do, but certainly it's worth stating this fact at this point, that the only abundant, democratic primary energy supply in Europe, and of course throughout the world as well, is sunlight, is solar energy. And just one second. So the global mean of solar energy that reaches, in this case, I'm showing the data for just the EU surface, is 5.5 times 10 to the power of 15 kilowatts per hour per year. That means that we only use, from the second data, what is the primary energy consumption, how much of this primary energy we use per year, and it means that we only use 0.3% of the solar input. So of course we want to shift this balance to be more sustainable, to be more environmentally friendly, and to really change the way that we live and we treat our planet. What I'm involved in, with a number of scientists and more industry involved in this change of paradigm that is really happening right now, not just in Europe, but throughout the world, is how to produce fuels and chemicals with sunlight. So how to tap into the solar energy so that we could convert solar through some direct conversion process into fuels and chemicals. And of course, in order to do that thermodynamically, sensibly, and with the good efficiency that would allow this paradigm shift, how we produce energy on our planet, we need to use some optimized, very clever molecular systems that would allow us to do that. And we can do that either using chemical catalysts, synthetic catalysts that work as well or even better as the biological catalysts, which are able of capturing solar light and using it to drive the reductive chemistry. And of course, we want to use highly abundant molecules that are available in the atmosphere and the crust of our planet Earth. So we want to do all these conversion processes using simple, highly abundant resources, such as water, carbon dioxide, and atmospheric molecular nitrogen. We can, of course, use solar energy indirectly. You all know, probably it's the case in Austria, certainly in Germany, in France, even in Poland, despite the a little bit of a lag time here with these technologies. We can obviously tap into solar energy when the sun is shining to produce solar electricity. And we do that through PVs, photovoltaics, and wind farms. we can also collect solar energy using solar collectors to obtain high temperature and heat. And some of this heat and high temperature can be used again for electrochemistry. This concentrated solar power is helping with the electrochemical processes with thermochemical conversion of solar into fuels and chemicals. So this is, as you can see, we've got quite a vast array of technologies that can allow us with, to produce fuels and chemicals using solar light. The problem is that, of course, solar intensity and the presence of availability of the solar energy varies constantly. So what you really want to do is to store the energy in the form of chemical bonds. And the only way of storing and transporting this energy on long distances is, of course, through conversion, chemical conversion into fuels and other chemicals, commodity chemicals, base chemicals, or high-value chemicals. And what I will talk about for the majority of my talk is this direct conversion that I'm focusing on, and as you can see a lot, as you will see in a moment, bigger and bigger groups of scientists are already taking a direct action to speed up the technological readiness of these direct conversion technologies, and the approach is called artificial photosynthesis. So just to sum up, the main goals of solar technologies, whether we're talking about these indirect solar technologies or whether we talk about direct solar conversion technologies, is to produce solar fuels, solar chemicals, but also a third, last but not least important goal is to remove and recycle carbon dioxide from the atmosphere, in line with all these policies and very brave steps that especially Europe is taking nowadays. You might have heard about the Green Deal, a huge investment into mitigation of the climate change and strengthening, establishing a firm model of sustainable and circular economy in Europe by the year 2050. And of course, we need to deliver these technologies now in order to be able to implement them by 2050. This is basically how implementation of any new or technology that is underdeveloped requires. It requires a lot of time. The technological approaches, I've already talked about electrocatalytic conversion with renewable power, and I'm just giving you the example of the scenario that already exists in Europe. Actually, this is the site that some of you might have heard about, Leuna Chemical Complex in Saxony-Anhalt, Germany, where effectively various inputs of energy, solar energy, are used in order to perform very complicated chemistry with the use of huge electrolyzers. So in other words, so let's start from this part of the slide. So renewables in the form of PVs and wind farms feed the solar electricity into the grid in an on-grid, off-grid fashion, of course. And this electricity is used to power electrolysis, water electrolysis, using huge electrolyzers into hydrogen, which can be used as a fuel itself. But very more importantly, it is an energy vector that can be used for chemical synthesis of many much more energy dense fuels, which are carbon-based fuels. I will show you the examples of them in a moment. And of course, the beauty of this installation is that you can use the existing liquid fuel infrastructure in order to transport these solar chemicals on large distances. And just as a back of the notebook, I'm giving you some values here. So with this particular installation is able to harness 560 gigawatts per hour of electricity to produce 280 gigawatts per hour of fuels. And that is enough to fuel 6 planes, 2,000 trucks, and 50,000 cars. So the two other approaches, I should mention that that approach that I've just talked about has a technology readiness level very high. We're talking about TRL 8 out of TRL 9 maximum technology readiness level. So it still needs some optimization, but it is really already very well advanced. Much more disruptive technologies, which are even more exciting, are the direct conversion technologies that I talked about a few minutes ago. So this is using photoelectrochemical systems that work just like the leaf does. So they conduct water splitting on one side, on the anode, we call it a photoanode, that's where oxidation processes take place. And on the other side, they conduct reductive chemistry. That's where the reduction of either protons into hydrogen occurs or carbon dioxide into solar chemicals and fuels occurs. And ideally, you want these to work at the atmospheric CO2 pressure and at room temperature or ambient temperature, maybe slightly elevated temperature. Elevated temperature definitely helps with catalysis, but you obviously want these systems to work in real life. You know, you don't want to pump a lot of energy into heating up these systems into very high temperatures as it is done in the chemical synthesis of, for example, methanol. The two systems that are used are either all solid state tandem heterojunction devices, as shown here, or the classical photoelectrochemical cells where you have both electrodes separated, connected by electric circuit, and separated with a proton permeable membrane, because of course you want to deliver those protons and electrons coming from water splitting reaction occurring on the anode to the cathode. The third approach is probably the most disruptive approach, but giving us the vast possibility in terms of chemical synthesis that this system can never deliver, because this system can deliver only very simple carbon-based molecules. These are the biological systems. So metabolically engineered microbial factories, which are predominantly based on microalgae and cyanobacteria, but also on other types of biological microorganisms, such as, to give you an example, anaerobic soil bacteria that have been very successfully used for production of target chemicals in for example, short chain alcohols that can be used as fuels, and they are fed with atmospheric carbon dioxide, but also with electrons and protons coming from water splitting occurring in inorganic photosensitizer that is decorating these bacteria, or they simply grow in the presence of the electrode anode that is able to perform the water splitting. And this particular approach has been called very fancy, in a very fancy way, but I really like this name, the bionic leaf. What is the state of the art of the direct conversion technologies? Well, this is probably, well, most definitely, actually, not probably, but most definitely, this particular monolithic photoelectrochemical tandem heterojunction device, which operates in the visible part of the spectrum with a very good solar to hydrogen conversion efficiency of 19%. We're talking business now. 19% is it's a very good conversion to start scaling up this technology to the industrial applicable level. I really don't have much time to talk about the natural photosynthesis, so I'm really going to skip these slides, but I just wanted to show you that, of course, nature found a way to the energy problem that basically drives life on our planet. And just wanted to mention this particular couple of very important nanomolecular machines that provided a blueprint for artificial photosynthesis. That's the water splitting enzyme and the photosystem 2 and photosystem 1, which energizes water-derived electrons and protons for the reductive chemistry. There are certain lessons from nature that one should definitely remember about, that you can't really get away when you try to devise a very efficient artificial photosynthesis system. These are the lessons that all the chemists and physicists and biologists, of course, have to remember when they devise the devices. So you need 2 photons for generation of sufficiently high redox potential for water oxidation. It's very important. I don't have time to go into it, but thermodynamically, if you want to minimize the overpotential, so in other words, the energy input into your system, which should be really minimal, you really want to your system to work on solar only, then you really need to have 2 photons to carry out the full reductive chemistry. You want to apply multi-electron character of water splitting, as well as carbon dioxide or proton reduction during catalytic reactions, just as it is happening in photosystem 2 and photosystem 1. You want to spatially separate the oxidation reaction and the reduction reaction, because it is really very important to minimize the back reactions, which always decrease the efficiency of any photoelectrochemical systems. A very important aspect is the efficient management of, it's called in business or in the field of photosynthesis, proton-coupled electron transfer, in the field of chemistry, in fact, proton-coupled electron transfer, again, for the thermodynamic properties and the stability of your catalyst. It's very important to get this process as optimized as possible so that your catalyst would work with the optimal turnover frequency and turnover number, so the stability and activity. And also you want to have, just as it happens in the photosynthetic cells, self-organizing and self-renewing catalysts, which are embedded in the smart matrix that optimizes the functionality of these catalysts. We're very lucky because we've got crystal structures, medium to near high resolution structures of the catalyst for water splitting, so the photosystem 2 and photosystem 1. You see that they're very big macromolecular machines that have been optimized for this process. This is the famous Z scheme that you all must have heard, maybe even in the primary or secondary school. If you don't work on photosynthesis, the famous Z scheme where you have the formation of the very high oxidizing potential in the reaction center of photosystem 2 and formation of a very low, so very good reduction potential in the reaction center of photosystem 1. And of course, you have the downhill energy flow through a series of very well optimized cofactors that allow the electrons derived from water upon absorption of solar energy in these reaction centers of photosystem 2 and photosystem 1 to end up in your final kind of effector of the whole process. And of course, we don't have time to go into it. You all know that, of course, it's NADPH in the photosynthetic organisms. The important thing that in that Z scheme, photosystem 2 and photosystem 1, so the biological catalysts, they work with a very high quantum efficiency, close to unity, like no man-made system. So what we want to do in the artificial photosynthesis systems, we want to tap into these high energy electrons from the primary reactions, photosynthetic reactions, and we don't want to produce all these complicated molecules of life that photosynthetic organisms do. And of course, at every step of the biochemical reaction, you have big energy losses. And therefore, the efficiency of natural photosynthesis, when you consider solar to biomass conversion, on average it's 0.2%. You can go up to maybe maximum 4% in such special type of plants or algae, microalgae that are grown in superbly optimized conditions. But really, you don't want to, you want to do much better than the natural photosynthesis does, and you want to achieve the benchmark efficiency of your artificial photosynthetic devices of at least 10%. So this is just the artist's impression. I will show you some real examples of the so-called artificial leaf. It is this heterojunction tandem device that does that mimics the action of photosystem 2 on the oxidation side of the leaf, that performs very efficient charge separation, so generation of holes and electrons upon absorption of solar light, so a kind of artificial photosynthetic center and it could be the semiconductor. Here I'm showing a very well known, and since the 70s, it's been known that this particular semiconductor is able to conduct water splitting reaction, but you have to shine UV light on it. So of course, the whole bunch of research goes on to improve the catalytic properties of this particular material, titanium dioxide, and decorate it with a light harvesting antenna so that the catalytic reaction could be performed in visible light. And of course, you want to mimic hydrogenase, or if you're really ambitious and you want to go for the highest energy and highest density energy fuels, that is the carbon-based fuels, you want to mimic Rubisco, of course, on the cathodic side. So the key issues is to improve the light harvesting of solar photons to 90% ideally. 70% is the absolute minimum for the system to have the overall efficiency above 10%. You want to base your devices on cheap and earth-abundant materials that are stable in water under various irradiation conditions. You want to really nanoscale a very efficient, we call it direct electron transfer. Effectively, you want those water-derived electrons upon absorption of solar to go into the right place and do it very quickly and efficiently, i.e. to your catalyst that is able to fix CO2 and convert it into a useful product, for example, methanol, ethanol, propanol, you name it. You want to obviously scale up your devices once you've optimized all these previous conditions, and you want to have very efficient use of the Earth's surface and urban space. We don't think, at the lab level about these issues too much, but really it's very important to think about scaling up of your most promising technology to a custom-made use, So basically, whether you want to devise a technology that is suitable for the backyard use, on the rooftop use, or whether you want to have the technology that is suitable for the large-scale industrial installation, as the one that I showed you at the beginning of the talk. A very important aspect, always overlooked by the scientists who are very focused on the on the modules of the artificial leaf, but very important to consider when you think of scaling up your technology, is to have the high energy return on energy invested index. And the last but not least, very important, as the history taught us, you want to convince the society at large that your technology is acceptable, is safe, is acceptable. It really improves the quality of life, even if it costs at the beginning slightly more. So of course that is an interdisciplinary endeavor that scientists and engineers together with the industry have to team up, and we've done so recently. Over the years, we've been working very intensely together with the Commission to boost the progress in the state-of-the-art and beyond state-of-the-art technologies based on direct solar conversion. And the program is called Synergy, and now it's called also Synergy. And I just want to show you a film that basically summarizes everything that I've said so far. Have a look.
Within Synergy, we want to develop a large-scale initiative with international appeal. And we currently have about 30 partners and 300 supporters from various origins, actually from academia, industry, from the society as a whole, governmental bodies. And why we want to do this? Because we want to find an alternative to fossil fuels, sustainable and also competitive alternatives to fossil resources which we currently use to make the materials around us, including fuels.
In long run, CeNT technologies, when fully optimized and developed, will provide negative carbon dioxide emissions, which means we'll be able to recycle carbon dioxide from waste to useful materials.
To achieve the goals in the Clean Planet European Strategy and the Green Deal, we need to exploit all climate mitigation options as well as breakthrough solutions and technologies. Thus, we urgently need large investments in research and innovation to upscale fossil-free solutions.
It will take 30 years to achieve a global ecological transition. We need to deliver now what we have, and within 10 years it will be possible to transform a successful industrial development into a successful product.
So then you saw it, right? Then obviously we want to develop the model for Europe that is based on fossil-free technologies and that it works in a circular manner so that you can close the carbon and nitrogen cycle. So then for the last maybe a couple of minutes, I'm running a little bit late. Just want to say a few words what we've been working on in terms of developing biohybrid systems for solar conversion. And then they work effectively like the chemical, photoelectrochemical cells I've already talked about, so I won't be repeating it. But basically we use photosystem or hydrogenase or other enzymes like dihydrogenase based biomolecular devices. Because as I already told you, in terms of photosystems, harnessing solar energy, they optimized for energy collection and charge transfer. They self-assembling and self-renewing catalysts for water oxidation and hydrogen or carbon reduction reactions. They're cheap to obtain. We can obtain them from large cultures of microalgae in really very big amounts for making thin layers in our biomolecular artificial leaves. And of course, they don't contain anything toxic in them. An example of a current state of the art is this beautiful recreation of Z-scheme, photosynthetic Z-scheme, using photosystem 2 on the anode, together with some fairly advanced photosensitizers, as well as the mentioned earlier titanium dioxide artificial reaction center, the semiconductor that is able to generate hole and electron pairs. Together with the hydrogenase, this is the enzyme that is able to reduce protons into molecular hydrogen on the cathodic side of the device. Another example is decorating nanoparticles of titanium dioxide with the hydrogenase, that these particles are additionally photosensitized so that the whole catalysis, water splitting catalysis, would occur in visible light. And this is the example, decorating these photosensitized titanium dioxide nanoparticles with a carbon monoxide dehydrogenase, which reduces carbon dioxide to carbon monoxide in visible light. So a very beautiful study. What we do in our group, we use photosystem 1, and not just any photosystem 1, not the photosystem 1 from spinach from the market, but really photosystem 1 from extreme extremophiles. Extreme, I mean the microalgae that grow at pH 0.05. We grow them in the lab at pH 2.5, and moderately high temperatures of about 45 degrees Celsius. The reason, as you know, those of you who work on biotechnology and those of you who do any molecular biology, you know that the most efficient and stable enzymes come from extremophiles. So this particular complex is very stable under very high irradiation when it's taken out of its natural environment from the photosynthetic membranes, and it can be successfully interfaced with various types of electrode materials, and it can operate for a long time, up to 1 year, with the intermediate illumination. We haven't tested the system for obvious reasons under continuous light for such a long period of time, but nevertheless, with the intermittent illumination, it can very efficiently produce solar electrons. So another example that the system that we've started to develop is the photosystem 1 that has been immobilized on the semiconductor electrode surface that is coupled with the catalysts, chemical called the so-called molecular catalysts that are linked with its particular domain, so that the electrons coming from reaction center could reach this catalyst very efficiently to conduct in this case, I'm showing the hydrogen production reaction, but there are other catalysts that we're exploring that can fix and convert CO2 into methanol. The rational approach, this is really what this disruptive technology requires, whether we're talking about biomolecular systems or whether we talk about fully synthetic photoelectrochemical systems. You do need to have a rational strategy how to minimize short-circuiting, back reactions, all these processes that hamper the efficiency of solar conversion. So the way that we do it with photosystem 1 is to either apply clever tricks with immobilizing it, taking advantage of inherent charge heterogeneity of the surface of this complex, or to use molecular recognition approach with another protein, would you believe, which is stable from the same extremophilic algae, which we can this time overexpress in E. coli, as you obviously do, because you want to have a load of this protein very easily expressed, but also having a histag that the biologists of you know very well is used as an affinity tag. We use it not just for purification of this protein, but on fixing it on the organic interface that is conductive and that it contains the famous NTA molecule that together with a cation, divalent cation, such as nickel or cobalt. We've explored various different cations because that's also an important consideration when you think about as efficient direct electron transfer as possible. But divalent cation together with a histag of a cytochrome and then linking the cytochrome in the oriented manner with photosystem 1, because it can bind with photosystem 1 only with one domain that is close to its photochemical reaction center. So we kill two birds with one stone. Okay, so we orient PS1 and we also immobilize it on this bioorganic interface. This is just an example of the system, very exciting project where we used our extremophilic photosystem 1 to photosensitize a very cheap narrowband semiconductor called hematite. Similar to rust, it's a little bit more fancy because we've nanostructured it. But this green stuff is our photosystem 1, and it allows hematite to split water in visible light. Normally, it's not very efficient in red light, but we made it to work in red light thanks to photosensitization with photosystem 1 in an oriented manner. And we constructed photoelectrochemical cell. In the aqueous buffer, we obtained continuous hydrogen production. Protons coming from water splitting, and the process was very efficient and allowed for production of decent amounts of hydrogen per hour. Another type of surface was on a different type of a semiconductor that you all know and all have in your pockets and on your desktops, silicon. P-doped silicon, again, the same strategy for oriented immobilization. And then this oriented immobilization really works because we've got manifold higher photocurrent production when we oriented photosystem 1 so that the electrons would flow efficiently from the electrode to the cathode. And this is a really beautiful example how physical phenomena can help biology. Here we've used plasmonic or plasmonogenic nanostructures. What are plasmons? The clouds of electrons that migrate in your nanostructures, metallic nanostructures, either gold or even better silver. We've used silver nanowires here. And we've, again, in the oriented fashion, immobilized photosystem 1 on it. And what we've got, to cut the story short, we managed to make our photosystem 1 absorb the green part of the spectrum. Because if you want to have this improved light harvesting efficiency of your system, you want it to absorb throughout the entire solar spectrum. And of course, the green stuff doesn't absorb green. So we've made our photosystem 1 absorb the green light thanks to these plasmonic interactions.
I'm very sorry to interrupt, but we have quite a lot of questions, so please.
Right. Literally, I'm wrapping up the last 2 slides. This is just to show you another type of exciting nanostructure that we've interfaced photosystem 1 with. Everyone heard about it, I have no doubt, graphene. In this case, we use single layer graphene, so really atomic thickness layer graphene, where we performed very clever tricks of forming molecular wires, either by covalent modification or by non-covalent modification of graphene. So we got homogeneous electrode coverage. We built in plasmonic nanostructures into this lattice, this time not nanowires, but silver islands, but we got the same effect, improved solar energy conversion. This is just to show you some data. You can all see it because it's all published, some of it quite recently, but this one is from a couple of years ago. Oh my goodness, that we have a really significant boost of cathodic currents when we have oriented immobilization of photosystem 1 on such graphene-based systems, and with the plasmonic nanostructures, even more so. Really huge, now we really got a huge amount of current compared to what we got when we didn't have these plasmonic nanostructures. So this is just a summary of our rational approach. I've already said that, so I won't repeat myself. It's too technical, I think, but nevertheless, obviously you want to develop, like in any disruptive system, a rational approach how to improve the efficiency of your system. And the way that we did it was through oriented attachment of the catalyst, homogeneous coverage, improving functionality and optical properties of your light harvesting catalyst, and of course, improving the direct electron transfer by some clever tricks that I certainly don't have time to go into. This is to do with these additional redox centers in the bioorganic interface. Okay, so that's the obviously work of many people. I've listed them all here. So very interdisciplinary research, great fun, lots of surprising and exciting discoveries that we've made on the way. And thank you very much for your attention. I'll be very happy to answer the questions now.
Thank you very much for interesting talk. So we collected quite a lot of questions. So, I would like to start with the first one. So, what is the water consumption for artificial photosynthesis? If used in large scale, could it raise an issue of water supply or sustainability?
Yes, it's a very good question, and thank you for this question. Of course, you want to perform the full analysis, life cycle analysis, and the energy use analysis in terms of the water consumption. The current trend is to build large-scale installations to use atmospheric water, you know, the water vapor, right? Water vapor that is, or moisture that is available in the atmosphere, so that we wouldn't have to tap into very sometimes limiting water resources, especially in certain locations on the globe. So certainly collecting, condensing the moisture from the atmosphere is one important aspect that needs to be covered. Of course, in the laboratory, there are no limitations in water supply. But an important issue for all the solar technologies is to develop circular models. So of course, as you know, burning of any fuel, carbon-based fuel, will generate carbon dioxide and water, right? And ideally what you want to do is to recycle those products of using your fuel so that they could be fed as substrates into your system. So this is really what the game changer in these technologies will be, to develop the systems that are capable of doing so.
Thank you very much. Another question is, which percentage of the area, for example, of Austria, do we need to use for solar energy harvesting to cover our energy needs with these biofuels?
Okay, so these are not the biofuels that are coming from biomass. I just wanted to make sure that it is clear, because the biomass conversion is extremely energy costly, and of course there are some very interesting ideas in the field that would help with reducing energy costs of these technologies, but it is still a disruptive technology. And of course, I'm not talking about second or even third generation of biofuels, because this is basically that's not what artificial photosynthesis is about. It's about direct conversion of solar into products. So the area that would be required to meet the energy needs of a particular country, continent, the world, of course, depends on the efficiency of your system. The lower the efficiency, the larger area is required. Nevertheless, if we're able to build on what is the state of the art in this technology, this 19%, for example, 19% of solar to hydrogen conversion efficiency, then certainly we can decrease the area that is required more than 100 times compared to what we would have to do to meet the same energy demands, for example, with biofuels. This is the 2 orders of the magnitude difference. And in fact, if you're interested, maybe I can ask the organizers to post the publicly available resource that the Synergy Consortium has developed. Actually, it was the Sunrise Consortium that subsequently teamed up with another consortium to form the Synergy. The roadmap that discusses exactly this aspect. What are the energy needs as in relation to efficiencies of the solar technologies? But certainly the high efficiency is important.
Mm-hmm. Thank you very much. And another efficiency related question, is it more energy efficient to use biosolar systems than conventional photovoltaics and batteries to power cars?
Well, you know, photovoltaics, batteries have a limited lifetime. You know, they cannot store the energy forever. Okay, and of course there is a large program in Europe happening right now as we speak, and it's been going on for quite a few years to improve, of course, the batteries. But of course, as you all know, batteries contain this is the technology that has inherent problems in itself, not just the storage problems, energy storage problems, but also the heavy metal problems, the using of the highly alkaline solutions inside, you know, the safety problems, etc. These will be all obviously targeted. They are targeted. They are being optimized, but it will never allow for the stable storage of solar energy. This is intermittent storage of solar energy. And what direct solar energy allows to do is to perform a long-term storage of high energy density molecules in the form of fuel, or of course, if it is a feedstock for chemical industry, commodity-based chemicals, right? Base chemicals. So that's, you know, these chemicals would be produced not via costly fossil fuel dependent, high temperature, high pressure technologies that are currently used for making most of the fertilizers in the world, or making processing fossil fuels for commodity chemicals for chemical industry, but it will be done using a sustainable model based on direct or indirect solar energy.
Mm-hmm. Thank you very much. And since you also talked about safety, so on the other hand, may the biological production of fuels cause biological hazard?
Well, of course, you have to always consider any hazard when you develop the technology. You want to make it, compliable with the health and safety regulations. The beauty of using microalgae is that you can grow them in open ponds. You can manipulate the growth conditions to maximize the productivity, because you want to get as much biomass as possible, so that then you could do the downstream processes. And of course, a lot of, especially in the biodiesel field, a lot of work has been done on doing exactly that, the optimization of the culturing conditions, the bioreactor design, whether it's going to be at the open pond or whether it's going to be the closed thin layer cascade design. These are all considerations that will have to be subjected to stringent health and safety regulations, for sure. When we talk about the most disruptive technology that I talked about, the using the microbial factories for production of fuels and commodity or high value chemicals, then of course we've got an issue of using genetic engineering, because you want to perform metabolic engineering in these cells. And of course the open pond option is probably not a good idea, but then you can still work on your bioreactor design to maximize the safety of your system and also the productivity, light harvesting, and also the biomass productivity of the system.
Thank you very much. So we already ran out of time. So additional questions could be also answered on Q&A window, or we can also post some in the chat. So maybe if Joanna Kargul is still here, then you may answer these questions there. So I would like to thank you again for interesting talk and your answers. And next we have a coffee break, so we will resume in 4:30.